Let's consider a data structure with a particular set of requirements. It has to be able to be traversed in sorted order reasonably quickly. It has to be able to insert and remove elements reasonably quickly. And it has to be fast to search for a particular element. The most intuitive solution one might immediately come up with is to have a linked list which is sorted upon insertion. What I mean by this is that when you modify the add step of this linked list, instead of inserting to the start or the end of the list, you traverse to the right place in the list and you insert there. For example, we have a linked list of integers which goes 1, 2, 4, 5, 6. We need to insert the number 3. We go 1 is too small, 2 is too small, 4 is too big, that's where 3 goes, before the 4 and after the 2. Makes sense? It's sorted at all times. We always have it sorted. To search, we just traverse through until we find the right number because it's sorted. We know that if it's if it's going to be larger than the first number, it's going to be further along the list. If the number is larger in the list and it's not there, it could work, but it doesn't seem that fast once it gets really big. Let's take one that's 1,000 length. We have to search quite far through that 1,000 length list to get anywhere. And that might not be optimal. Maybe there's something more efficient we could do. This is when we have to consider the use of our references, our pointers in these nodes, and what we could do with them. Do we just have to have one, or can we have multiple? And can we make some rules about where these pointers point to, which will help us in this endeavor? Well, what if we made our rules such that they helped us traverse this list in the most optimal possible way? And what if we just had a more helpful number of these references? Let's say that our nodes can point to 2 items. And let's make the rule that one of the items is less and one of the items is greater. You'll see very quickly how this can be useful. Let's start off with just one node at the top here. This node will have a value of 5. And let's say that the left node is less and the right node is bigger. So since the left node is less, we want to insert 3. We start with 5. 3 is less than 5, it goes to the left. Make sense? Simple. If the right is larger and we want to insert something to the right, let's say we're inserting 7, and now we have 7 to the right. So it goes 5 and then 7 if you try to find the largest element. To find the largest, you just go right, 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 right. Find the smallest, you just go left, 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 left. It's quite simple to find the largest and the smallest. But you might be wondering, what if I have a number that's larger than 5, but smaller than 7? It has to go to the right of 5, but then what does it do? Well, keep in mind that this is a recursive sort of data structure. Every node has these 2 references. So we go 5, well, 6 is larger than 5, goes to the right. 6 is smaller than 7, so it has to go to the left of 7. So it goes 5, 7, and then to the left of 7 is 6. But now you might be wondering how we can make a useful traversal out of this. How do we get this into sorted order? Well, the sorted order question actually becomes a lot simpler if we consider how our recursion is done. We can traverse the list. It's not actually a list, it's nonlinear anymore. We can't really call it a list. We can traverse our nonlinear data structure, our tree, in such a way that we get into sort order by going left, center, right, or right, center, left. The way we can do this is we can follow through. Let's say we want to go largest to smallest, because that's where our tree right now is a little bit more complicated. It's a bit of a better example. We go to the rightmost node to get the largest for the start. And then what is the second largest? Well, the second largest is going to be what was the center of the subtree that the largest is in. What does that mean? Well, remember this data structure is recursive, so every node can be considered the root of its own subtree. Let's visualize the subtree of just the system with the largest node. That subtree has its center node, its lesser node, and its greater node. But what do we know about the subtree? We know that every one of the nodes in this subtree is greater than the nodes above it, because it was on the right of the node above it. So we know that it must have been larger. Since we know that it must have been larger, we can say that it is indeed all larger. We just have to traverse this subtree in order. And to traverse this subtree in order, we go furthest to the right, then we go to the center, then we go to the left. And remember, when I say in order, I mean largest to smallest. So right, center, left is the in-order version of that subtree. And then we go through every other one of the subtrees, and we go right, center, left, right, center, left, right, center, left, until we get through the whole tree and we get it in the correct order. We go left, center, right if we want the opposite order of that. So if we want smallest to largest, we just go all the way to the left to get the smallest, then center, then right, left, center, right, left, center, right, left, center, right, and we get the smallest to the largest. How do we search? Well, at every step, we simply ask ourselves the question: is the one we're searching for less than or greater than the current node? So if we want to have another binary tree, let's say this one has a root of 0. And then, well, we know that negatives are going to be on one side and positives on the other. That way we can say, is our number negative or positive for the start? And let's say on one side we got -5, on the other side we got +5. Right? That's what our tree looks like right now. And I'm deliberately only telling us about the nodes we can see. We can only see the root, the left, and the right. That's all we need to see. Because we don't care about what's on the rest of the tree. That could be really large, really small. We don't care. We just care about what we're searching for. And let's say the number we're searching for is -3. So we go 0. Is it -3 positive or is it a negative? Well, it's a negative. So we can go, okay, it's towards the side of -5. But it's larger than -5. So it's got to be to the right of -5. So we go center, then we go left, then we go right. And what's the right of -5? Well, in this case, it was indeed -3. And then this sorting algorithm, the searching algorithm, I mean, can be applied across the board. To search through the tree, all we need to do is just ask ourselves, is it less than or greater than at every step? And if it's equal, that is a separate case, but it's not much different. We just have to set a condition that one of them also takes in the equal. So one of the sides is less than or equal to, one of the sides is greater than or equal to. So hopefully this made binary trees a little bit more clear and understandable for you guys. Good luck. Hopefully it helps with your coding. The tutorials do cover the coding implementation of a binary tree, and hopefully that'll be useful to you. Thank you so much for watching. Enjoy your day. Hello! So today we will be going into the methods of the binary tree, and we'll be figuring out which ones are faster and which ones are slower in different cases. I understand a lot of people have had trouble with things like recurrences, understanding how fast things go, getting an idea for the runtime efficiency of a method by looking at its code, especially when there's various cases, best case, worst case, involved. It requires a pretty good understanding of what the code is doing, so let's get into it. We're going to do this with the binary tree today. That's what we're going to start out with. So here we've got our code. You have to clone this from GitHub. I'm going to send the GitHub link to the chat. Let me just get it really quick. Alright, GitHub link is in the chat, so you guys can clone the project, and while you do that, I'm going to explain what we're doing. So last time we wrote the binary tree. The binary tree was written here to basically be a binary tree. And now we're going to test out various methods. Some of these methods don't really depend on how the tree is shaped. Their speed doesn't really depend on it, right? And some of them do. What I mean by this is some of them, when they're given what's known as an unbalanced tree, are going to run much slower than ones given a balanced tree. Or even faster, depending on the situation. I'm going to demonstrate this by running a few more tester methods, but first I have to come up with a way to make a tree unbalanced. So let's just let's create a static method which takes nothing as an input and gives us an unbalanced or a balanced B tree of a certain size. The first one I'm going to make is for the random one. This one's going to be hopefully quite balanced. It's random, so it might become unbalanced, but when you're adding 10,000 elements, the odds of it being unbalanced are pretty low. So let's do that. Let's call it public. No, I'll make it private, actually. Private, static, B tree. It's called a binary tree. String, build, balanced tree, and it's going to take a size as well, so it's going to say long size. And to build a balanced tree, this is actually all we have to do. We have to add random things to it. So here I'm adding random things to the tree that are within the spec of this size. And this is going to hopefully add so many random elements that the tree is going to have a lot of stuff on both sides of its root. That's the goal. It's the balanced tree has a lot of stuff on both sides of every node. So every node of the tree, remember the tree is shaped like a bunch of nodes, should have a reasonable number of stuff on both sides. That's what balanced means, and this randomizer should hopefully accomplish that. So return B tree. Right. So now that's how we make a balanced tree. We make it random. It's the same thing we've been doing before. Now let's make an unbalanced tree for the left. Or for the smaller. I'm going to call it smaller because left and right are kind of subjective for this. So we're going to call it build unbalanced tree increasing. And now here, instead of using a random, I'm not going to use a random. I'm just going to say I I'm just gonna cast I to char here. So this is just gonna make the character from the index, and then get rid of this randomizer at the end as well. I'm just gonna add it with nothing. It's just gonna be not there. Now this is gonna create a horribly unbalanced tree because it's gonna be sorted like every item is gonna be considered larger than the previous. That's what this method here does. And in fact, I'm gonna cast this to char as well, just to be sure. Char I. Perfect. So that's our unbalanced tree increasing. Now decreasing is going to be similar. I'm just going to reverse the loop. So I'm going to say build unbalanced tree decreasing. I'm going to start at the size. And I'm going to go down to 0. And I'm going to do I minus minus. So that's just the reverse of the for loop I did before, and now here I'm going to do the same thing. So now we have two ways to get an unbalanced tree and one way to get a balanced tree. But before we actually use these for speed testing, I just want to actually see, well, what these trees look like. What does it look like to be balanced? What does it look like to be unbalanced? Let's demonstrate. So here I'm going to go into my main. Where's my main? I'm just going to call the three methods with a size of like 15. Let's just call it build balanced tree 10. And actually, well, I should probably save it. So I'm going to say binary tree string balanced equals build balanced tree. Binary tree string. And if you're wondering how to write a binary tree, last tutorial was covering that. Tutorial Thursday. Monday covered it too, but it wasn't so succinct. We're going to call it small unbalanced equals build balanced tree increasing, and now binary tree string big unbalanced equals build binary tree decreasing. So now if I run these three, I'm going to put a breakpoint right here so I can actually view what these trees do in main right now. So we have our binary tree from last time, and we're trying to figure out when the binary tree is balanced and when it's unbalanced, and what exactly that means for the speed of our various methods, if you're familiar with the whole binary tree concept from last time. Here we've got binary tree left and right, and a balanced tree has lots of children on the left and lots of children on the right. So it has children on every side, right? A balanced tree looks like it's quite full. It has a root node with things on the left and right, and it has left and right things with children on both left and right, and that goes continuously for as much as it can. Whereas an unbalanced tree looks like this other one here in the debugger, the small unbalanced, where all the children just kind of form a linked list. They just make a list that looks like this. The unbalanced one is a lot slower than the balanced one for some operations, and we're going to try to figure out which operations those are, but we can also try to figure out by inspection which operations are going to be fast and which operations are going to be slow. So would you be able to tell maybe how long it would take to get the smallest element or the largest element in a tree which is balanced versus the one that's unbalanced? Well, it'll probably depend on which way the tree is unbalanced and what you're trying to find. So here, our what's our smallest here? Our data here is of some value, right? It's harder to compare because these values are strings with weird characters in them. But if you go left, 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 that's a long traversal. You're basically traversing a linked list in O of n, right? So to find the data, which I think in this situation is the smallest, or is left larger? I think left was larger. I don't remember. I did this one last time, made the binary tree where I set my left and right rules. But I'm going to say lefty larger, just because that's what I think it was. So here to find the largest, it's going to be O of n, because you have to traverse the binary tree that's unbalanced through n items that are very long. But to find the smallest, all you have to do is return the root, because, well, there's nothing to the right of the root. So being unbalanced is simultaneously super fast, O of 1, and super slow, O of n, depending on what you're trying to do. That's sort of the thing with an unbalanced tree. Now, if we see the other way unbalanced, you can see that it's just the same, but it's the opposite side. So we'll step over. We'll get big unbalanced, so unbalanced small, unbalanced big. They're just the same, but they go in a different direction. So here the right nodes go right, 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 right. So it's going to be really fast to find something that's all the way to the right, but it's going to be really slow to find something that's, it's going to be really slow to find the one that's all the way to the right. It's going to be really fast to find the one that's all the way to the left. That's the nature of an unbalanced tree. But the balanced one, it kind of averages things out. To find the one that's leftmost only takes a couple of things. It's like 3 away. And to find the one that's rightmost only takes one step, but that's just because it came slightly unbalanced out of the randomizer. But mostly it's quite balanced. And now we can see what methods are affected by being balanced and which methods are being affected by unbalanced. And we can try to understand why. So here if we do a benchmark and we call it for add node unbalanced, so name equals add node unbalanced. And the category is going to be binary tree, just so that that is set. Now public static long test add unbalanced long input. We're going to create the binary tree. It's going to be binary tree string tree is equal to build unbalanced tree. I'm going to say increasing, and it's going to be on input. And now we're going to say make the string that we're going to add to the binary tree. So here it's going to be one that is larger than the largest one from the increase. So here I'll just copy paste this, and I'll make tree.add. I just want the string itself. So I want it to be input plus 1, input plus 1. So it's just the one step after that, and then we can say long start time equals system.nanotime and tree.addS. Now we're just adding to the unbalanced tree something that's even more unbalanced. Minus start time. Alright, and now we can see if we run it how add compares to add unbalanced. Let's see which one is slower and which one is faster. So we'll reset all of this. We'll do add node, and we'll do add node unbalanced. Now we'll see if we turn up our steps per iteration all the way, which one takes longer and which one takes shorter. Now we can see that add node is still potentially, that's really weird, and I think add node unbalanced just decided to clonk out on me. Why is that? It's probably causing some kind of stack overflow already from being, it's a stack overflow. So in fact, add node unbalanced is in such a bad state that it has to call the recursion so many times because it has to traverse such a long list that I think it doesn't work unless I did something else wrong. Add node unbalanced, it's a stack overflow. So stack overflow arises when you have too many recursions and you can't actually fit that in your stack. So maybe I'll do a less steps per iteration on the unbalanced method. But that in itself demonstrates why unbalanced tree can be quite problematic. That's because here, we can see add node unbalanced is much slower when it's actually able to operate. It has to add it to the really long linked list. And because we're doing this recursively, because we're going through our tree in a recursion, we can ignore those spikes. That's when it starts stack overflowing. So it stack overflows pretty quick. I'll have to reset it to not get it to stack overflow. It has to recurse, like 18,000 times to add it properly. Whereas on a balanced tree, the tree gets wider as it gets longer. So you don't have to do these super long traversals to get to the last node. It acts a lot faster. So here we can see quite the speed difference. We can pretty much ignore those spikes. They're unrelated. And soon we'll get to the stack overflow on unbalanced. There it goes. And unbalanced is bad because it'll cause stack overflows if you have a very large data set like 18,000. But more accurately, in most situations, what it'll cause is a significant increase in the runtime of this method. So that's balanced versus unbalanced. But we don't actually need to run the speed tester to be able to tell what's going on with that. If we actually go into binary tree, we can see exactly what's going on with balanced versus unbalanced. We can see that the binary tree has all these various methods which recurse. And we can try to understand how many times these recursions happen. So let's go into add and let's try to understand when add is going to recurse, how much it's going to recurse in which case. And maybe we can try to bound it by some kind of upper bound, lower bound kind of deal. Let's go into our easiest case first, which I actually think is the stack overflow case, the unbalanced case. That's the same as a very inefficient add to a linked list, where you're, instead of going head.next equal, or instead of saying head equals whatever, replace the head. this add is doing a different thing, where it's actually traversing the list and adding to the end. That's if it's unbalanced. So the worst case, if we think about it, is if we take the longest path that we can, so we take the most steps in our binary tree, like the most lefts and rights we can take, and then we do it. And now what is the most unbalanced we can get for a tree? Well, technically the most unbalanced, the most steps we could take, is so that every node only has one child. That's the most unbalanced possible situation, right? Because we can't come up with a situation which is more unbalanced than every node having one child, because that way, if a node has multiple children, that skips a node in our traversal, that makes it faster. So the slowest possible situation is if the node only has one child. Now, what else do we know? Well, we know that if the nodes only have one child, and in the worst case we're adding to the end of the nodes, if we're adding the new largest element, that's going to take O of n. So we can say here that it's probably going to be a worst case, so worst case O of n, where tree is completely unbalanced, and we add the largest or smallest element in the direction of balance. If that makes sense. Now, what's the best case? Well, if we think about it, the best case is also when it's very unbalanced. The best case would be when we're adding to the tree, but there is a minimum number of children there, right? We're assuming the tree is sorted, right? Oh yeah, we're assuming this is a binary search tree. So we're assuming that the binary tree is, when you add, you add the nodes such that it is following the convention of a binary search tree. I can show you that, actually. I've got a demonstration of it, a GUI one from last time, where we can maybe visualize it, and probably would be nice to bring it up. So I'll launch that now. Let's see if it'll launch in a reasonably timely manner. So yeah, here. So we're going to assume that the binary tree follows a certain order, and that is that the children are added based on their compare to score. So if we implement the comparable interface, we're able to give a score to an object, which determines where it falls in the tree. And in a binary search tree, what we're doing is we're actually adding based on the left node is if the score, well, in this case, left is smaller, right is bigger. In mine, lefty larger, because it's like an easy thing to remember. But it really doesn't matter which one is left or right. The point is you add one of the ones that's bigger to one side and smaller to the other side, which speeds up our search. So here, this is an example of what one of these trees could look like. And if I bring back IntelliJ, and I bring back that window, because shaking them makes them go away, you can see here that the traversal to find the, well, to find the smallest, you just go smallest, right? You just go left, 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 left. You can do that with a while loop. To find largest, you go like right, 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 right. And when you're adding, you're just finding the correct place for the item to go, and you're adding it to that place. So here, we can actually get to the best case of adding if we look at this. What would the best case be in this situation? Well, I think the best case, right, would be when there is no node to the side of the root you need to add to, and you just need to add it to here, which in that case, it's O of 1, right? If I add 240 to this, it's going to be O of 1. I can demonstrate that, because if I make something here with a score that's really high, like 242 here, it's going to add just right here in O of 1. So I'd say our best case, right, is going to be O of 1 when, so best case, O of 1, where you add to one of the sides of the root that is null, right? So that's our best case and our worst case. But we also have a most common case, which isn't really the best case, nor the worst case. And that's kind of what we can see when we follow the speed tester. The most common case is harder to understand because it depends on our data set. It's kind of hard to tell, right? And the way that they mathematically prove it, they can prove it inductively, but all you prove depends on the shape of your tree and like how it was arranged. You could just be very unlucky and you could have an unbalanced tree that's really slow. You could be very lucky and have a balanced tree that's going to be O of 1. But overall, you can tell because it's a recursive algorithm. And most of the time, in this sort of tree, if you just spam add randomly, and this is, I'll spam remove, I'll get it emptied, and then I'll spam add again, it's going to slow. Oh, yeah, it doesn't like spam remove when there's when I remove more elements that are in the system. So I'll just restart that. There we go. So here, if I spam add here again, on a more reasonable tree that didn't start off with a really large value, we can assume that it has a similar number of nodes each time. And we can assume that the add method will work in about the same amount of time as the search method. And we can say it goes roughly n log n, O of log n kind of deal a lot of the time, because it has to do it the same way as search, where it goes through and through and through. But really it's bounded by n, and its best case is 1. So it's really hard to say the exact situation. But what you can do is you can calculate it quite exactly if you know the shape of your tree. Or if you have something like a heap, where your tree follows rules, like a heap follows the rule of each node being full at every level. If you have a heap, then it's actually possible to know your expected efficiency. But with this kind of chaotic linked tree dataset, it's hard to know the exact average runtime. It really depends on how your tree is arranged. So now we can go into some other methods and we can try to understand how they run, because some of these actually don't depend on any of these particular situations. Some of these run in their own way, and these are things like in order and reverse order, and in turn, because iterator uses them, iterator. So let's see exactly what in order does. It says if the temp is not null, then it's returning the temp. If the and if the temp get left is not null, it returns the temp.left. It does a tree traversal such that if I have a smaller tree than this, I'm just gonna remove some to make it, prune the tree a little bit, get it to be a more visible graph, increase the widening so you can actually see it. So if we go through, what this traversal does is it gives it in order, because it goes left, 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 then it goes left, center, right. It's going to say add the left one, 2, add the center one, 16, add the right one, then go, this was the left already, so then go center, no right, center, left, center, right, left, center, right, left, center, right. It's going to go left, center, right forever and ever and ever. And well, we can see how many steps it takes. It probably, I'm going to guess it takes the n steps, right? Because it touches every single one of the n nodes in the tree. Right? I'm going to guess it's going to be O of n in the worst case, or in the best case, in every case. But if we really want to be sure, we can use a counter. So here we can say, well, we can just use the debugger to view this, right? I'm going to say int in order, I'm going to make it a field so that we can update it from multiple places. I'm going to say int in order counter. So now I'm going to say in order counter equals 0. And every time I'm going to access this, I'm going to say in order counter plus plus. And this is going to count how many times in order was called for every time it is called. So return in order counter this, and then we're going to, well, actually, maybe I'll say working stack equals that. Then I'm going to say system.out.println in order counter plus space plus working stack. And then I'm going to say return working stack. All right, so this way, when I do an inner traversal, it's going to tell me how many times the recursion was called and how big the tree was when it was called. So, oh, I forgot to say dot size. Rerun that now. But hopefully we can already kind of see a pattern even just from this. Well, we'll wait for it to rerun. Come on, IntelliJ, don't misbehave on me now. Yeah, so now we can actually see that not only did our guess of it being O of n check out, but actually when we run it and we count the amount of times we do the recursion, it actually lines up to be n. Not O of n by how fast the method is running, but it actually lines up to be O of n based on this counter. And keep in mind, we're doing a completely random data set, so our tree may be completely unbalanced, our tree may be perfectly balanced, our tree may be all kinds of different trees. But no matter which kind of tree it is, in this situation, we can view that it is O of n. But remember, I didn't need to use a speed tester, and I didn't need to do this to figure out it was O of n. All I needed to do was have the logic of, how many times is this called for a given tree? How many times do we like in this tree, do we call this method on? Do we call it on every node? Do we call it on, log of every node? What do we do it? And here we call it on every node, and we can see in our printout that, yeah, it just goes through and it reports the, reports this has to be O of n. no matter how large it gets. And hopefully that's a relatively convincing rationale behind it being O of n as well. And that's a technique that is pretty valid to use if you were to do something like an assignment or a quiz and you want to know if your method is more like, from a mathematical perspective, working in O of n or whatnot. You can do it that way. And that way when you actually run your method, you can tell whether it's running in O of n or whatnot. But the reason we have the speed tester, the reason we test the actual milliseconds, is that a lot of the time students may forget to put a counter in certain methods, so they won't necessarily increment the counter every time that they touch something, but they may increment the counter, incorrectly or not keep track of it very well, and it can be sloppy as well because the counter may not take everything into account. For that reason, or like the counter may not take into account, like if you call an O of n method from an O of n method, that it becomes n squared, the counter won't take that into account. So you have to really be careful about where you add these counters, and that can be hard to do, especially in a more complicated method. And for that reason, it wasn't encouraged over using the speed tester, but it's also a good technique for counting. We just know here, since it's recursive, the counter being put in this method, and this method is the only method that is called, then it can be pretty reliable. All right, so now we've identified O of n when the other one was bounded by O of 1 and O of n. So in the worst case, it was O of n, and in the best case, it was O of 1. But yeah, we could also definitely count how many times this recursion happens in the same way using our counter, and then we can get our average case, like our expected case. But expected cases don't mean too much in this case because, well, it is indeed a chaotic sort of data set. Now, smallest and largest are similar to add in terms of their runtime efficiency, but they're more obvious than that because you can really tell when they're the most efficient and when they're the least efficient based on the visual of the graph. Like you can see here, add and remove or not add and remove, get smallest and get largest really does depend on just the linked list here that is formed between the root node and the smallest, or the root node and the largest. In this balanced tree, they both run at a similar speed. Here it's 4 for a tree of size 18. And here it's 3, or yeah, it's 3 for a tree of size 18. No, here it's 5. 5 steps for a tree of size 18 versus 3 steps for a tree of size 18. So you can see roughly where it lands for a average case, sort of like just as a ballpark. It lands, I would put it somewhere on log n speed for an average case, but don't quote me on that. That's just kind of like a my vibe reading of it. But if we want the actual best or worst case, we can find that just with the same logic as with add. Where with add, we saw that the best case would be if there's just one node. So again, if there's just one node on that side, so if there's only, if there's only one node on a given side, so here in this case, like one node, if we find largest, that's O of 1. Or if there's no node there, it's also just O of 1. It's smallest, right? So the best case of smallest and largest would be no nodes present except for the smallest and largest. So we say no nodes present except smallest and largest, O of 1. Oh, exclamation mark. So best. Right? And worst is going to be along the same lines as before, O of n. Same logic as well, because it has to traverse a linked list. O not O of 10, O of n. Has to traverse a linked list-like thing from root to largest. So yeah, those are like the best and the worst cases of these various methods. And then there's also things like find. Did we ever write a search method here in this binary search tree? I'm just going to double check. If not, I can write one now and we can look into that as well. Main, test binary reverse order. Huh? No, I guess we didn't. Okay, that's fine. Well, we can totally get a find. We can call it like find node, and it can be a helper method. And we can say find node given data. So we can say here, private tree node e find, and this will be e data, and this will find exactly where the node with the given data is. So now we can say it's going to be the same logic as add. In fact, we can actually copy paste a lot of add to use the same sort of logic. Where is the recursive step for add? So here, well, actually we have to add the recursive step for this too. So it's going to be private tree node e not dot, get rid of dot. Find recursive e data tree node. Excuse the lag. Current. Oh, I cannot send a lag. Come on. Current. Okay. And now I'm going to take, it's not the exact same logic as add, but it's very similar. So I'm going to say current dot get data is greater than 0 if, yep. Okay, current dot get left is null. Now, well, actually, I'll call the find method recursion from the non-recursive public method first. So I'm going to say return find recursive data root, and that's because we're starting on the root. So now if the node is greater than 0, else, and now we ought to compare if they're equal as well. So we're going to say if node, or if current dot get data dot equals data, we will return current. Now if the data is towards the left, then if the node, if current dot get left is null, well, instead we have to say, well, we'll throw an exception, or we can return null because there is nothing in the tree that is like that. Because it's a binary search tree, we know that if the node doesn't follow the rule, like if it's not going to be to the left when it's supposed to be, well, it's, in that case, it's null. And then here we can say else find recursive data node dot left. Current dot left. Now same thing here, find recursive, but now we just do the same thing with the right side. Now there's a lot of symmetry in binary trees. That's why That's why we do just the same thing for the left and the right, and in this order, it's quite a symmetrical data structure. So most of what we do is just doing something to the left side and then doing that similar thing to the left side. So here, if current dot get right is null, instead of setting right, we say return null. And now we should have all of our various return statements, except we'll just do one post recursion as well. So now we should be able to find an element given the data. Now, just to make sure that that works, I'm going to add that to our test suite, and we can then try to figure out how fast it runs. So we've got our trees here. Yeah, cool. So after this, I'm going to say tree node e. Let's call it middle of list. Not e. It's going to be tree node string. No, it's Pocket Monster. We filled it with Pocket Monsters. Forgot about that. Middle of list is equal to tree dot find list dot get list dot size over 2 over 2. Oh, it's going to be called B tree. There we go. That should work better. Why does it not like that? Give me a second. Where's my tree node? Did I call it tree node? I did, and it's public, right? Oh no, I might have made tree node private just so that I increase encapsulation. No, I'll make it public. Excuse me? Why you don't work? Whatever, I'll make it a static class. That'll make my life a little bit easier for today. And then I won't have to reference it from a specific object. Let's just do that. Tree node. Tree node bucket monster is the middle of list. And now I can just view that by doing system.out.println middle of list. Now let's see if our thing runs. That's not the right thing to run. I want to run binary tree.main. And that's also how you search in a binary search tree. Let's make sure it works. It's gonna take a second to run. Nice. Score of 126 urine is the strongest thing in our set. But I actually just wanted to see the middle of list, which is right here. Oh, it's null. Okay, so it doesn't like something about my find method. Let's peep it out. Find. Where are you? Find. Find. There we go. Come on. And a debug. So if it's on that side, if the current left is null, if the current.getData equals that, return current, else you traverse the tree to that side. If the current left is null, then yeah. Okay. Now there's a better way to handle this actually. We can say if current is null, return null. And then we can say here, instead of this, that. And that way, we should have a better system. And the reason it failed there, I think, was because I forgot that return statement. This return null is unreachable now, as it should be. Okay, this should be a better method now. That is more clean and hopefully more functional than the previous one. And here we're able to find a node given a bit of content. And it's a very simple method because we're using a binary search tree, which is it's sort of the point of the binary search tree is to make this sort of thing easy. Well, that's one of the points of it at least. Now we'll go up and we'll find it in our tree here. And, oh, I should actually do the explanation on stable versus unstable sorting algorithm there. So it finds the reference to it. I don't have the printout. We can use the debugger to view the details, but it just finds the node with the same content. What is the runtime efficiency of this? Well, the runtime efficiency of this will depend on the shape of our tree, obviously. But we will also be able to say we'll be able to count our recursions. So here we can say a counter. We will call it a find recursive counter. So int find recursive counter equals, we'll make it 0. And now here before I run, I'm going to say find recursive counter equals, no, find recursive counter equals 0. Now every time we enter the method, we want to be able to increment our counter. So we'll say find recursive counter plus plus. And then when we're finished, we will be able to figure out what our find recursive counter was. So we're going to say tree node e found is equal to that, and we'll dot out println tree size is size plus counter is find recursive counter. And this way we'll know how many times the recursion happened for the given size of our tree. And now we'll return found. This is kind of similar to what I do with the speed tester with the actual exact runtimes, but this time it's a bit more rigorous because we're actually using a counter that counts the amount of times the recursion happened. So here, find recursive, yep, okay, cool. Then we're printing that out. Let's do that, and I'm just gonna make this happen a little bit earlier so that we don't have to scroll through as much. And I'll get rid of this print line, which tests the iterator, because we know that that's gonna work. So just comment that out completely, and well, we don't even need to really test the sort either, so we'll just fill it, and we'll see how long it took to get to the middle of the list, how many steps it took for the size of the tree. We'll run that. It takes a second because it has to fill the tree and the list, and filling it can be quite slow at times. Tree of the size is a size 150 and counter is 13. So we can see it's nowhere close to our worst case of O of n, but it's also a lot worse than our worst case of O of 1. And that's what we can roughly expect. Now, if we say log of 150, we want to say log base 2. So I'm just curious how close we're getting to there. 7.2. So it's not quite at log base 2 of 150, but I'm guessing it's going to be somewhere around O of log n for our average efficiency. And we can test that by just trying this a bunch of times. Instead of for list.getSize over 2, we could just do it a bunch of times randomly and find the ratio. So we can here print out the ratio of the size, and we can sort that list. Actually, yeah, it's a long process, but and we're getting to the end of our time. So I'll leave that as something, as like an experiment you could do, is that the pseudocode for maybe figuring out a better graph of runtime efficiency would be, or for like an average case, so a better way to find average case. So have a data set that is long and random as heck. Then you're going to say, take note of how many times you recurse for size of tree with a random element. Then you watch the numbers change as size ++, and then find the ratio between size and number of steps, and then plot. And then you could probably average that a lot. Average the above a lot from many runs, and that is how you could find the quite a bit more accurate runtime complexity of something on like an average case, kind of like a general tree, right? Because we can find through math or through our understanding what the general average case is going to be for something like one of these operations, but well, we don't have, unless we have a given tree, unless we're given the shape of our tree, we can't find the, well, maybe we could find the average case if we were very, very, trying very, very hard, but really it's not trivial to do that. So what we could do instead is you do something like this, where you watch the numbers change, and then you find the ratio between the sizes, and then you average them out. Then you can get a better trend. If you have any questions, I'm happy to answer about any particular topics, but maybe this gives an intuition on some of the runtime efficiencies of a tree. So yeah, although I said it was O of n or O of 1 as our kind of lower and upper bounds for runtime, it's actually realistically going to be somewhere closer to n log n most of the time. I was gonna get to heap sort today, but I was quite carried away with the whole explaining the understanding and the calculation of runtime efficiency and how many steps various things take, and writing out these tests for balanced versus unbalanced tree. So I think I'll be getting through heap sort the next time. So we can do that twice, it's no problem. I'm not even sure what is being referred to with making me do something twice. It's quite all right. But yeah, I'll get to heap sort another day, probably tomorrow. Or not tomorrow, probably Thursday. But for now, the runtime efficiency thing is here. We've got a search method, we made a find method, and we explained kind of the logic and the math behind how some of these sorts and how much some of these not sorts, how much some of these traversals and stuff work. So again, our in-order traversal, our reverse order traversal, these ones happen in O of n because they visit every element exactly one time for each element. Our add method here goes best case O of 1 because it could just add next to the root, or it could add somewhere far along the tree in O of n if it's very unbalanced. Then our find method, well, our worst case is going to be O of n, our best case is O of 1, because it's the same as add. I literally copy-pasted add to write find. So it was very, very similar. Then we have our smallest and largest methods, which similarly are O of 1, best case, O of n, worst case. Right? And that depends on the balancedness of the tree. So again, a balanced tree is a tree where it has lots of children on both sides, and an unbalanced tree is where it has a long chain. That's a lot about the trees. Now, coming into heaps, which are going to be next time, is heaps have some properties which help them avoid being unbalanced and help them have a better worst case, as well as having a better best. Like their trees or heaps are generally just better than trees in a lot of ways. They're more optimized, but they're slower to do some things. Like they're just a different data structure. So a heap has certain more rules that it follows. We know how a binary tree, kind of like the no rules. A binary search tree has rules upon addition, where when you add to a binary search tree, it has to add to the correct side given the compare to value of the various nodes. Then a heap has additional rules, which we'll learn about next time, where it actually adds subtrees based on, well, more rules. And then it makes sure that it's balanced, and it makes sure that it doesn't have these long chains. In fact, a heap is not often even implemented using a tree. It can be implemented using an array as the sub-data structure because of how the symmetries of it line up. You can use an array to implement a heap, and it's quite a good way to sort. And then, last thing I wanted to touch on today, I know I'm going quite over time to touch on it, but it's hopefully all right, is indeed it's the idea of stability for a sorting algorithm. There are stable sorting algorithms and there are unstable sorting algorithms. And we ran into this last tutorial when we compared binary tree sorting. So when we just in-order traversed a binary tree as a sorting algorithm, not really technically a sorting algorithm, but well, it does sort things, so you could call it one. We compared binary tree sorting to using a merge sort. And we viewed that although both sort in a valid way, the binary tree sorts in such a way that the order of items is not preserved. What I mean by this is if you have two items which have the same value, let's say you sort playing cards by their number and they have different faces. If you first ordered them by face and then sorted by value, something like merge sort would actually preserve the order of the faces while only reordering based on the value. It only reorders based on what you sort by, right? Whereas tree sort, as well as heap sort and quick sort, all of these various sorting algorithms don't take that into account. Those various sorting algorithms sort in such a way that they actually don't preserve the order of what was once in the data structure. Like if you sort playing cards by value after you first arrange them by face, by like the the house of the card, whatever, the one that makes it like the hearts or the diamonds or whatever. That'll not be preserved in heap sort or in binary tree sort or in quick sort. And that's an important detail. It's one of the many reasons I believe in merge sort supremacy, but that is a tale for another day. That's just a little extra detail from last tutorial to help explain why my initial test for the binary tree had failed, because I was, instead of using compare to, I was comparing the dot equals of two things in the sorted data sets. And I was seeing that the dot equals comparison was failing, and that's because order is not preserved after sort in this sorting algorithm. I don't think that's within the scope of Comp 250, but it's just a little detail to help explain that previous situation maybe a little bit better than it was previously explained. So yeah, open to questions now, if you have any. Otherwise, I think I can leave it at that, and that will hopefully be helpful for future content. Specifically, I know a lot of the quizzes ask about the details of how fast things run, and in terms of like their best and worst case, and maybe they give you a case and they want you to know how many steps it takes. I think heaps are going to be what's focused on for the runtime efficiency, probably, if I were to guess. But I'm not too sure because I don't write them. And then with trees, most of the time for add and stuff, it's best case O1, worst case ON. All right, well, thank you very much for attending. It's been a very fun time. Next time I'm going to be doing over the heap and the heap sort. All things heap are happening next tutorial. Maybe I'll try to visualize it as well, because it can be a confusing topic sometimes, using an array in order to hold like a tree, kind of. It's a tree, but it's flattened down into an array. Whatever. We'll understand it very well next time around. And I do encourage anybody to watch the short animated video that plays at the start of these about the binary trees. That should hopefully make it more clear as well. Thank you, and farewell.